In the last of Chapter 7, we'll look at some examples of Runge-Kutta methods and see how we can easily construct the iterations for each problem, whether they be first order or higher order. And in example 7.3 on page 256 and 257, you're asked to use a second order Runge-Kutta method. A second order Runge-Kutta method is the modified Eulers that we just discussed in the previous lecture. So we're using the modified Eulers method to integrate y prime equals sine y with the initial condition y of 0 equals 1. And we are to integrate from x equals 0 to 0.5 with step sizes of 0.1 and looking at just keeping 4 decimal places for each of our approximations. So just following the formula we had for modified Euler the last lecture, we simply just start off by just recognizing the fact that first of all, y is just one-dimensional, it's not a multidimensional vector, and that the right-hand side, f of xy, is simply sine of y. And our step size is given as 0.1, so when we do the first step to get k0, we will make sure that we use 0.1, and so ultimately this is what we'll start off with. K0 will always be 0.1 sine y, depending upon where we are with y. And then the k1 constant will be defined this way, where we'll have to make an adjustment to x, increment y, and evaluate f again. But this results to this. So whatever we get for k0, we're going to plug it in here, take half of it, add it to y, evaluate the sign at it, and then multiply with 0.1. And then that will be the step. So that will be our increment to get our new approximation at x plus h, which again will be 0.1. So it's fairly simple to just, from software standpoint, the user just provides sine of x, and then you just use the integrate method appropriately for this second order Runge-Kutta method. And if we go to the next slide, what we'll see is just some hand iterations of this. Again, you start off with the initial condition y equals 0, y equals 0 equals 1. And so we just simply start off and plug that value in for the sine of y, in other words, in the y value into the sine, and we get our first k0 is this value here, 0.0841, and we're going to plug that in for the, remember, the value for k0 and the k1 constant, evaluate the sine appropriately, multiply by our step 0.1, here's our new value. And then we add it to where the initial condition, which is 1, and so here's our new estimate of what the solution looks like at 0.1. And then down here, we're just iterating again. Again, you start off with where you are, plug that into the sine, get the new value here for k0, plug that in to the function there, and update k1 appropriately. And then again, keep in mind we are moving from, we were starting off at y equals 0. We took a step to 0.1, and now we're up to 0.2. So this is the value we had for y of 0.1. We add our increment, and then this is our new estimate for what y is doing at 0.1. So it's fairly straightforward to do that iteration. And in the next slide, you'll actually see a set of tabulated results where, again, the initial condition was given here, and we've already obtained this approximation, and we're just continuing on to see what we would get finally when we get to 0.5. We get this value. Turns out the exact solution written in an inverse way of x in terms of y, you could write it either way, but in this case, if I give you a y, what would be the corresponding x? And we can see that it matches up perfectly. So the modified Euler is doing a wonderful job of matching up in 4 digits, decimal digits accuracy at the point x equals 0.5, which y should be 1.4664. Now if we move on to the next example, 7.4 on page 257, 258, Here you're asked to use the fourth order Runge-Kutta method to integrate this second order differential equation. Keep in mind again, you'll notice, look at the highest power of the derivative, it's 2, so it's the second, it's a second order ordinary differential equation. And again, we solve IVP problems only here. We're not doing boundary value problems, so that means you'll have the function and its derivatives at the same point. So we know that y of 0 is 0, and when we are given that y prime of 0 is equal to 1, you're asked to integrate from 0 to 2, so we're going to go to 0 to 2, and we're going to go in steps of quarters like this. Okay, so this is how we're going to step through this. We're given steps of h equals 0.25. Again, this is not a first order ODE, so if it's a higher order, you have to convert it to a system of first orders. We do that with these standard substitutions, the variable substitutions. We will always let y0 be y, let y1 be the first derivative, and so forth. In other words, the subscript matches the derivative, like that. Okay? And so the first equation will always be this form, y prime of 0 equals y1 by definition. And then if you take the derivative of y sub 1, that would be the same thing as the second derivative, which is given by the differential equation, and you will replace that y prime with y1. So that's our f right-hand side function. It's a vector-valued function because it has two components. And here's just the simple Python coding of it. Again, you can use an array, and you can use a list and return a list here very easily for both values. Okay. Well, I guess I should say that since we're using zeros here, which comes from the NumPy library, this actually is creating an array. F would be defaulted to an array with two components there. And so this is returning the first element array as y1, as it should, and the second element should be that corresponding term here in the f function. So that's pretty straightforward for this particular problem. Just looking at the rest of the code, again, set where you want x to start, where you want it to stop, build yourself an array for y, because this is a vector value function now. The initial conditions are what we're specifying y, so we have to have y of 0, which we said was 0, and y of, these are the components, and then y1 would be 1, which was the value of the first derivative at 0. So you're always going to have this, this structure for your initial conditions. And again, that matches the y, this matches the y prime, and so forth. So we set the step size to 0.25. Remember, we showed you the print solution, which is also a function available for your use to determine how often you want to print it, print results. And then, of course, all the functions in these modules are called integrate, pass the f function that the user creates, and the other appropriate values for the Runge-Kutta method, and then we'll output the results. And because we set frequency equal to 1, you would technically get a list of every single estimate of the solution, and as well as its derivative at every step. I'm not showing that because the table will be too large here, but keep in mind you're able to output what y0 is and y1 are each step, and we're interested in the solution. So so if we look at this particular value, you can see that it's getting closer and closer to around 0.5. And one thing to realize is that, remember, the Runge-Kutta methods were described so you wouldn't have to construct all those representations of derivatives that you had for the Taylor series methods. And so it's kind of nice to know that if you had used a Taylor series method and constructed all the derivatives for all those expansions like we did earlier, you'd actually get the same value as the Runge-Kutta method, which is so much easier to use. So this is just a test that both methods would be appropriate, but the complexity of doing Taylor series is that, remember, you'd have to redefine using the ODE and the solution vector itself y, you'd have to reconstruct all of the derivatives, which can be complicated, tedious, and you probably could get it wrong. And another example, which is kind of an interesting example that illustrates some behaviors that you can notice sometimes when you're solving ODEs. This is 7.5 on page 259, and we're going to use a fourth order Runge-Kutta method to integrate a very simple ODE. It's first order, so there's no need to create a system of first order ODEs. It's first order itself. So it's just y prime is 3y minus 4 e to the minus x with this particular initial condition to select that particular solution. Keep in mind, we use initial conditions to pick out a particular solution because there's many solutions that differ by a constant that satisfy that differential equation, and that particular initial condition picks one out. You're interested in integrating from 0 to 10, and the step is 1/10. And amazingly enough, the actual analytical solution for that IVP, for this particular IVP, is just y equals e to the minus x. Okay. So that means you have an intuitive idea what that solution is going to look like. As x is, if we just think of a simple Cartesian coordinate system and think about, as x is certainly when x is equal to 0, we're at the value 1. Okay. And as x is very negative, we know that we would be blowing up and getting larger and larger. But as x gets very positive, it's converging down to 0. So it's gets very, very small in the limit. So if we were to do this numerically, again, assuming we don't know that analytical solution, we're just going to pretend we didn't know it, we would construct our f function appropriately that describes the right-hand side, set our limits of integration, build, we only have one initial condition, so technically y is just an array of one element, which is fine, just for consistency with the inputs to this integrate function. Because h is kind of small here and we're integrating to 10, we want to see every 20th result in our output table for our function in x. So we'll set the frequency at 20 and call the integrate function for the Runge-Kutta method. This is using run underscore cut4.py. And here's what the output would be. Remember, we asked every 20 iterations, and this is going up through 10. Again, this is in scientific notation, so this is 10 right there. And look very carefully at what the approximate solution is doing. Noticing these are the exponents over here, noticing it's blowing up. They're very negative, but they're getting extremely large negative. Does not look anything like you would expect e to the x to look like, right? E to the minus x, excuse me, to look like. So the question is this is what we call instability in the solution y. It's not matching analytically what we'd expect to get. So the question is what's really happening here? Is there something wrong with the software? Is there something wrong with our parameter choices? If we didn't know the analytical solution was e to the minus x, we could be in big trouble here. Okay, so let's think about what is the method reacting to produce this type of output. Well, one way to look at what potentially can be happening is looking at the general solution to the ODE. In other words, before the initial condition, this is the family of solutions. Every function that looks like this, constant times e to the 3x plus e to the minus x, satisfies this ODE. Just take the derivative, and you'll always get something like that, regardless of what the constant is. So suppose there's a small error, a slight perturbation, we'll call it epsilon, in the initial condition. In other words, what if we just shifted our initial condition just slightly off of 1? In other words, y of 0 equals 1 plus epsilon. Then what would happen to the analytical solution? Well, this is what would happen. The epsilon would be multiplied times e to the 3x. and then you would have this term here, plus e to the minus x. So clearly when there was no error, if there was no error like we had a minute ago, epsilon is 0, okay, and the solution is e to the minus x. So if there's just a slight perturbation in the initial condition, we have this term to deal with. But what's interesting, as x approaches infinity, that term will dominate this term. This term will get smaller and smaller, but this term will not, you see. Even though this epsilon is small, e to the 3x can be huge as x goes to infinity. So there's nothing wrong with the code. This is an example of numerical instability of the solution. The sensitivity of the initial condition, all right, specifies there's an issue here with this particular problem, not the code. So this is an example of an unstable solution. It wouldn't matter what method you used in this case, there's going to be some instabilities in trying to approximate the solution. So that leads us to the last part of the chapter here on this, just a brief discussion of what does this mean, stability and stiffness. If numerical integration is stable, that means the effects of local errors do not accumulate, and so the global error stays bounded. What we just saw previously with that particular ODE is the error does not stay bounded, it just gets worse and worse and worse. So stability has nothing to do with accuracy. There are inaccurate methods, actually, that are stable. So the stability of a problem is determined by the ODE itself, the method that you choose to solve it, and then sometimes the step size h. So it's not just always just the method or the problem. It can be the step size. So it's actually a combination of these three. And sometimes in a lot of physical applications and applied physics and so forth, you have to sort of analyze all three of these simultaneously to see how consistent your solution is, and if it can change slightly, if you slightly change the problem, change the method, or change the step size, and notice what differences that you see. So if we talk about the stability of a method, then maybe that will dictate, well, maybe there are certain parameter choices we have to be careful about when we use these methods, and I want to illustrate that with Euler's method. So if we were to look at Euler's method on this very simple ODE, okay, y prime equals, let's say, minus lambda y, with this initial condition y of 0 equals beta, then this is the analytical solution right here, that y of x then will be beta times e to the minus lambda x. So if we remember, Euler's method looks like this particular formula right there. In other words, to get our increment in our estimate of y, we simply take our step and multiply it times the derivative. But if you then use this ODE that we have here that tells us what the derivative would be, then you would plug that in for y prime and get this expression. So what that tells us then is that an advancement to get y of x plus h is equivalent to 1 minus lambda for some constant lambda, we'll assume positive, 1 minus lambda h times y of x. So if you think about the magnitude of this, right? So for example, if the absolute value of 1 minus lambda h is greater than 1, then it turns out this method would be unstable. Well, remember what the solution form looks like. Regardless of what beta is, and if we assume that, again, I'm going to make the assumption that lambda is positive, then this component right here, e to the minus lambda x, as x goes to infinity, gets bigger and bigger and bigger, that's going to go to 0. But if we're approximating and trying to follow what y will do in time, in other words, as we move from x to x plus h, if the absolute value of that is greater than 1, then our solution is going to grow away from 0. There's no way it's going to get smaller and smaller from a magnitude standpoint, either positively or negatively, okay? And so that's why we mean that this method would be unstable. There's no way it's going to be able to produce approximations that get smaller and smaller. So the method would be stable if this absolute value was less than 1. And you can show that just simply solving that. That means your choice of what the step size needs to be is 2 over lambda. So that will prohibit this factor here from being greater than 1. So what this means is that you can use Euler's method on this problem, but there's a restriction on how large the step size can be. If it's too big, the method has no hope of being able to approximate the solution accurately. So this is what we mean by the stability of a method. And you can do this for every method, but you have to think about it in terms of the ODE and the initial condition, is what we just talked about earlier. Stability is determined by the method you choose, the ODE you're solving, and its initial condition. So the last term that we want to talk about in this chapter is just so you know, and you may see this in some applications that you might work with down the road in any scientific application, is sometimes you'll hear of what's called stiffness, and an IVP is stiff if some terms in the solution vector vary more rapidly with x than other terms. And this second order ODE here, right here, y double prime plus these terms 1001 y prime plus 1000 y equals 0, is a classic example. Notice that the coefficients here, the factor on the y prime and the y are so much larger than the one on y double prime. That's a hint. You can show that to solve this method with the Euler's method, your step size would have to be exceedingly small, 0.002, to be stable. And so if that's the case, again, what happens is the solution may have a very erratic kind of behavior and then be kind of constant and things like this. This comes up very commonly in chemical reactions and so forth. And so it's hard for the ODE method. It can do really well on these kinds of regions here, but then it struggles, right, with a big H. And so what happens is you end up having to pick a step size that's very tiny, in some cases, but wasteful in others. So it really makes them very impractical for these kinds of problems if your solution looks something like this. One approach is maybe drop the order of the method from a higher order method to a low order method, but you're going to have problems with the truncation here. So it's just something to be aware of sometimes, that again, it's nothing wrong with the method per se, it's just this problem is going to require an extremely small step size.